Hello, we are Team 9 of Michigan Technological University Biomedical Engineering Department's senior design teams. Our project is titled Extremity Location and Movement Sensing for Movement Disorder Patients. It is estimated that 42 million people in the USA alone suffer from a type of movement disorder. The most common are Parkinson's disease and essential tremors, both of which cause tremors in the upper extremities. Take a moment to imagine if you couldn't drink from a cup without spilling or write your name legibly. Difficulties such as these are why it's so important to make sure that those affected by these disorders are treated with the best possible care. The progression and treatment of movement disorder diseases are monitored using qualitative testing. Medical professionals use tests such as the finger tapping test, supination pronation test, and resting and active tremor tests to determine how a patient's symptoms have changed over time. While these tests are good measures of disease change, the problem is a lack of standardization. There is no guarantee that each patient is scored the same way. Additionally, these tests don't give us a lot of numerical results. Together, these problems result in the lack of optimized therapeutic measures. By adopting standardization and quantitation for the monitoring of movement disorders, we will be able to gain accuracy and precision in test results, while also optimizing therapeutic measures and eliminating the guesswork in treatment plans. Using an inertial measurement unit and an Arduino Nano, we created a device capable of tracking upper extremity movements. Using C++ and Excel programming, we were able to use this device to collect, store, and analyze tremors during finger tap, supination pronation, and resting and active tremor testing. After gaining IRB approval for human studies, our team was able to test our device by gathering baseline and disease state data from volunteers. For our baseline data, the device was used on test subjects who were not diagnosed with any movement disorder diseases. The disease state data was collected from a test subject with Parkinson's disease who was using deep brain stimulation therapy to correct his tremors. The collected data was analyzed in both the time and frequency domains. The time domains show x, y, z, and rotational acceleration. Inconsistencies in the rate, amplitude, and/or width of the peaks can indicate the presence of bradykinesia and tremors. The frequency domain analysis of the datasets was done using a Fourier transform, which shows the different frequencies that appear in the data. Large peaks or lack of peaks in the frequency domain indicate that the patient was able to perform the test consistently, while multiple peaks in the data indicate tremors. Looking at the resting tremor results in the time domain, the disease state tremors resemble the baseline when the DBS is on. As soon as the DBS is turned off, the tremors increase in severity. The frequency domain analysis shows a lack of tremors in the X and Y baseline acceleration. For the disease state DBS on data, there are small peaks indicating that there were some slight tremors. Once the DBS was turned off, there are prominent peaks that indicate the presence of strong tremors. These trends are the same for the Z acceleration and X gyroscopic acceleration data sets, with the tremors being present in the disease state and increasing in intensity when the DBS system was turned off. For the supination pronation results in the time domain, even with the DBS system on, the subject's tremors had more variance in degrees of rotation compared to the baseline. When the DBS was off, the variance further increased and the frequency of movement was less consistent. The frequency domain analysis indicates consistent movement in the Z acceleration and gyroscopic acceleration of the baseline data. In the DBS on disease state, the Z acceleration shows that the tremors interfere with hand movement. The tremors are even more prominent when the DBS system is turned off. For the finger tap results in the time domain, there is an increase in noise and a decrease in the total number of taps for the DBS on disease state compared to the baseline data. The finger tap frequency is less consistent, however, the subject did better than the baseline in the average amplitude of their taps. When the DBS was turned off, the tremors impacted the finger taps and resulted in a consistent frequency of taps. However, the average amplitude decreased and the majority of taps were not strictly controlled movements. The frequency domain analysis shows consistent baseline finger taps. In the disease state, when the DBS is on, the finger taps are not consistent. There is a slight peak when the DBS is turned off as the tremors result in unintentional, yet patterned, finger taps. Our device is the first prototype in its line. Future Bluetooth integration would eliminate the need for wiring between the device and a computer, increasing the ease of data collection. Additionally, the scope of the project can be expanded to include lower extremity tracking to get a more complete understanding of patient conditions and to monitor a broader range of movement disorders. Finally, app or software development would make data collection easier for in-clinic and potentially even at-home use. This project would not have been possible without the mentorship, support, and knowledge of many individuals. We would like to thank everyone who has helped us along the way. If there are any questions, comments, or concerns regarding this project, please feel free to reach out to any of the listed individuals. Thank you for your time.